So we'd like to know what causes the line spectra. Credit is first given to Niels Bohr, who described these in about 1909 and said that the energy of an electron in an atom is quantized. Now, when we say that something is quantized, what this means is that only certain energies are allowed and others are not. And so one of the comparisons we can make is something like this. This is how Bohr envisioned his atom right here. Bohr envisioned his atom as having a nucleus surrounded by these orbits. And if we think about back to the construction of an atom, remember that the nucleus has which particles? Protons and neutrons, which means that they have a charge that is positive. The nucleus is positively charged. The orbits here would contain the electrons, which have a negative charge. And whenever you have opposite charges will attract each other. So, if we were to do an example, and I don't want to drop my block of wood anymore because it's already broken. All right, we'll just take it anyhow then. Okay, if I take my block of wood, I can have this block of wood in many positions. I could start with it on the ground, or we could start it up here, or we could start it way above the ground. And if I had to let go of this block of wood, what happens to it?
Falls.
It falls down. The reason why it falls down is because there's an attraction called gravity. And it's just like in an atom, there's going to be attraction between the negatively charged electrons and the positively charged nucleus. And whenever there's an attraction or a field of force between two objects, then we have the ability to have what's called potential energy. And the further apart two objects are that attract each other, the greater the potential energy between them. So if I start with the wood block here, or if I start it up here, we're going to have different amounts of potential energy that they could have. So with that in mind, then we want to know which position has the greatest amount of potential energy. There we go. And we'll pop it up here. Which position of the woodblock has the highest state of potential energy? If it's on the ground, or if we have it 6 feet off the ground? 5, 4, 3, 2, 1. And certainly if it's 6 feet off the ground, it has a lot more ability to do work than it would be if it's on the ground. So the further apart objects are, again, the more potential energy they have. So the same is true with electrons in an atom. If we talked about this being the Bohr model, ordinarily an electron is going to want to be in its lowest state of potential energy, which we would say is right here. That is its lowest state of potential energy. And we refer to that low state of potential energy as the ground state, just like if that wood block was on the ground. And again, that is its lowest state of potential energy. Now, ordinarily, this wood block is going to want to stay in its lowest state of potential energy. What do I have to do to cause it to come out of its ground state? I have to lift it up, which requires energy on my part. So the same is true with electrons and atoms. They will ordinarily want to stay in that ground state, but we could wind up running an electrical current through them, like this. Or we could wind up spraying them into the flame. When we do that, those electrons absorb some energy. When they do that, those electrons become excited. And we refer to that as an excited state. An excited state is basically any state other than the ground state. But just like this block of wood, if I put it up here and it's in a state of higher potential energy, if I let go of it, what's going to happen to it? it's going to fall back down, and ideally it would return to its ground state. Okay, so electrons are the same way. Once they get kicked up to this higher energy level by pumping electricity through them, they're not stable there, so then they want to fall back to a ground state. As long as I keep pumping electricity through there, though, those electrons are going to keep cycling down. They'll drop down, they'll go back up, they'll drop down. Each time that there's no energy that's running into it, it'll drop back down. Every time it drops back down, we say it goes through a process of relaxation. And once it relaxes or goes down to a lower energy level, it gives off energy in the form of light. And in the case of hydrogen, which was the very, very first one we saw here, with the lines in it, each one of those lines corresponds to a different jump. So the red line we saw was a jump from the third level down to the second. The bluish-green line we saw was a jump from the fourth level down to the second. And then the violet one we saw was from the fifth level down to the second. And so, again, these lines are quantized, which according to Bohr means they have very specific energies which cannot be changed. And we cannot have any energies between them. And what this ultimately led to is a description of this as called quantum leaps. And if you've ever heard the term quantum leap before, where is it usually used? Unless you had science, then you know this. If you haven't had any science, you see it in sci-fi. And who does quantum leaps? I know it's an old show now.
Star Trek.
Star Trek, you probably do. I wasn't a Star Trek watcher.
Star Trek does, Doctor Who does, various other ones do, Back to the Future does.
Right. And when they do them, the whole idea is that a quantum leap is usually popularized in sci-fi as a jump across space and time. It's a time traveler, exactly. And so the whole idea of the quantum leap came about, though, from what happens within the atoms. And the reason why it originated here, and here's the downfall of this theory is, and this is where it fell apart, is that in order for the electron to jump from here to here, it could not exist anywhere in between. It had to go instantaneously from one point to another, kind of as if it was time traveling, because it was an instantaneous occurrence. And sci-fi picked up on that, and they popularized the quantum leap as being time travel, when in reality it originated from these jumps between these quantized energy levels in atoms. 5, 4, 3, 2, 1. And it is in the ground state. So remember that when we talk about the atom, we were looking at something like this. Let's see, end of class the other day. Here we go. The energy level closest to the nucleus here is the first energy level, and this is the state of lowest potential energy. And once again, we refer to that as the ground state. Now, today what we're going to do is this. We're going to develop this idea a bit more. We call this the Bohr model of the atom. And the Bohr model of the atom, we envision the electrons circling the nucleus, kind of like planets orbit the sun. But one of the downsides, we mentioned this, first of all, the Bohr model really only worked well for the hydrogen atom. If we looked at more complex elements, that is, ones with more electrons, it just didn't work very well. So when we talked about this Bohr model the other day, it really only worked well for hydrogen. A second primary weakness, and this was a perceived weakness, it turns out later to be a strength, but one of the perceived weaknesses at that time was that we talked about the electrons jumping between these energy levels. Do you remember what those jumps are called? Quantum leaps, right. And the problem with the quantum leap, scientists recognized at the time, is that in order to jump from one level to another, it could not exist anywhere in between. It had to instantaneously go from one level to the next. And then we talked about how science fiction has popularized that, the quantum leap. In fact, that's where you probably hear about it more, the common person hears about it more, is this quantum leap as being these big jumps across space and time. But it originated in these jumps between these quantized energy levels. But each specific jump then, like in this case the third down to the second, or the fourth down to the second, or the fifth down to the second, this one here for the hydrogen atom, each jump corresponds to a different line that we saw in the line spectra. And each element had its own line spectrum because we talked about these jumps between energy levels would vary from element to element. And so we could distinguish them based on that. But again, another perceived weakness was the fact that it only worked well for hydrogen and that they could not exist anywhere between the levels, that the jump had to be instantaneous. So what happened was this, and what we're looking at here today all took place in the 1920s. And in the 1920s, there was a look at this dual nature of light, and we say that light has a dual nature. And by a dual nature, that means it sometimes behaves like a wave, so again, sometimes behaves like a wave, and sometimes it behaves like a particle. Most of light behavior is like a wave, and when we talk about what wave behavior is, waves do things like this. They go through constructive and destructive interference, which means that waves, when they come together, they can add together. That's called constructive interference. And sometimes waves can cancel each other out, and that's called destructive interference. In fact, if any of you wear these noise-canceling headphones, which I like to wear, especially if I'm outside or if I'm riding on an airplane or something, it cancels out the sound and it makes use of this destructive interference that cancels out the waves. And then there's the particle, and some other wave-like properties would be like reflection and refraction. You might think that when you look in the mirror as having a reflection of yourself, but that's really one of the wave properties of light. If you were to drop, say, a stone in a puddle or pool, and you see those waves migrating out, they run into a wall, those waves will start reflecting or bouncing backward when they do so. And again, that's a property of waves. But light also has particle-like properties. If you have a solar-powered calculator, anything with a small solar panel on it, it's making use of the particle property of light, because what happens is that when light comes down and strikes this surface, this panel on here, what it does is it causes electrons to be kicked out of there. And when they kicked out, if we continually expose it to light, they will continually kick out those electrons, and it'll kick out enough electrons such that it will cause an electric current to flow through the calculator to power it. So that makes use of the particle property of light. So what happened in the 1920s was this. We're going to look at the work of 3 scientists, and even though I don't ask you to remember names or dates, I still put them down simply to give credit where credit's due, and just to kind of put each of these into perspective. The first of these we'll look at is Louis de Broglie. And in about 1923, what he did is that he showed that electrons have some wave-like properties. And he reasoned something like this. He said that if light had a dual nature, that is, sometimes behaved like a wave and sometimes like a particle, perhaps when we look at these electrons and atoms, perhaps we can also think about them as waves. Even though we think of electrons as being primarily particle-like, they might have some wave-like properties if they move really fast within an atom. And in fact, de Broglie was right, because it turns out that the electron microscope was created in the late 1920s and into the 1930s, and it makes very use of this fact. And what we do in the electron microscope is we basically pass electrons through material, and we use it to magnify things to a very large degree. And so de Broglie was onto something. We had been thinking about electrons wrong all along. We'd only been thinking of them as particles. And so he suggested that we should also think about them like waves. Then there's another scientist, and some of you have actually heard of this name, probably not as a scientist, but you've heard the name Heisenberg elsewhere. Okay, who knows where I'm talking about?
Breaking Bad.
Breaking Bad, yes. Heisenberg, in that story, actually named himself after Werner Heisenberg, and the reason why is because Heisenberg developed what we call today the uncertainty principle. And so there's an element in that show, Breaking Bad, where he acted in a very uncertain or very unpredictable manner. And Heisenberg himself, this was about 1927, showed that it is impossible to simultaneously determine the speed and location of an electron in an atom. And so what this means is this. It means, and we're not going to show this one. This one we could actually, if we had time, we would actually show this one here. We could show de Broglie's equation. We could even get something out of it. We do some calculations that have some meaning. If I were to show you the mathematics associated with a Heisenberg uncertainty principle, you wouldn't get anything out of it unless you've had probably differential equations. Yes, ma'am. Go ahead.
You can't tell the speed and location. And how do you know that it jumps from the levels?
Okay, and that was a problem. That's what Heisenberg was really all about when he was saying this, is that we went back, if we go back and look at the Bohr model atom, this was too predictable. Okay, this has too much certainty with it. And so what Heisenberg was saying is that it can't be this predictable, it can't be this certain, we can't talk about it jumping those levels. So that's really what his mathematics is showing. So that's basically, he's trying to say that that's why this is wrong. Okay? But again, we can't really show the mathematics in here because unless we've had differential equations, we can't show really what that is. You'll just have to trust me on this one. And then there was a scientist by the name of Erwin Schrödinger. He developed what we call the wave equation. And he developed the wave equation in which the electrons were treated as if they were waves and not as particles. And again, the mathematics of this, I don't even understand anymore today. I understood back when I was doing the multivariable calculus and the differential equations, but having been away from that now for many, many years, if I were to go back and study the mathematics, I could get it, but it would take me a few days to kind of go back and get the mathematics of it. But what these two ideas showed is this, is that the Schrödinger wave equation defined what we call orbitals rather than orbits. The orbits being predictable, the orbitals being less predictable. So he defined orbitals rather than orbits to depict the locations of electrons in atoms. And we define an orbital like this as being a region in space where there is a high probability of finding an electron. So now, of course, this has to mean something, and it does. So again, you had asked Gabby about the jumping. Here's where that comes into play, and here's how we've defined it now. Here's how we're going to show it. Let's say, for an example, we were talking about a bicycle wheel. And if we took that bicycle wheel and we spun it into motion really fast, you could look through those spokes, and if it's spinning so fast, you cannot see the individual spokes in there because it's moving so fast. However, we know that there's a high probability of finding a spoke somewhere because all we'd have to do in the spinning wheel is put a stick in there, a finger, or throw a rock or something, and we'd wind up finding those spokes. And so those spokes wind up filling up a volume, just like an electron, this here representing an electron, this would represent an electron that's moving around within an atom. And when we say that an orbital is a region of space where there's a high probability of finding an electron, what this shading represents is areas where it's shaded more darkly is an area where it's more probable of finding an electron, and an area where it's less densely shaded is where it's less probable of finding an electron. So again, we're not talking about the details of exactly where an electron would be, but rather we talk about them as being probabilities of finding electrons. And again, where it's more densely shaded, it's more probable of finding an electron. Where it's less densely shaded out here, it's less probable of finding an electron. And what these represent up here is several different models of orbitals. This is a very simple orbital. This here is a more complex orbital. And this here is still a more complex orbital here. And what these models represent is where we would find an electron 99% of the time. They would be 99% of the time contained somewhere in the space. But where in the space we don't know, other than that it's highly probable of finding it in the space, and that it's more probable of finding it in places where it's more densely shaded than where it's more lightly shaded. Now what I find really amazing about all of this is that this is back in the 1920s when all this was developed. And when they were developed, these models were plotted out in 3 dimensions without the aids of things like computers and stuff to do calculations. You do one calculation, find out a probability, do another calculation, find a probability. And I don't know, who's the furthest in mathematics here? Anybody into calculus yet? Okay, so if you get into calculus, once you get into like a second year of calculus and differential equations are one of those things where when I went through it, I was proud if I could finish a problem in 1 hour. We would wind up doing several sheets of paper to do the calculations to come up with a result. And so the early scientists, when they were plotting these out, each one of these positions in these models would have come through a separate calculation where you calculate it, you plot it, and then you'd be plotting these things out in 3 dimensions. And so the time it must have taken for those early scientists and what they were thinking when they developed it is just something I have a very huge admiration for, because it must have really taken lots of time, first of all, to think of it, and then to do the calculations that went behind them. But one of the things that it showed is that if we look at a simple shaped orbital, something like this, is that these orbitals, a simple shape, are a whole lot like the orbits we looked at the other day. An orbit that has a small size would have had an energy that is smaller than an orbit of a large size. The same is true when it comes to these orbitals. A small orbital would have been one with low energy, and a large orbital would have been one with a larger energy. It's just we don't know the details of where they moved. And they weren't moving these specific orbits, but rather it was probable of finding them somewhere in those spaces. So that much is what the size does. So the size still corresponded very much to the sizes in these Bohr orbits, except instead of saying that they had to move in these circles around here, they could move anywhere in those spaces when they moved around. Now the second thing you're going to see up here is that I have orbitals of different shapes. And so now, how is that related? Well, what I have here is a couple models of vibration patterns of a string being plucked. And this is actually only 2 different patterns of literally thousands or an infinite number of patterns that could develop. But anybody hearing music? Okay, if we listen to these 2, what's the difference in these 2? What would we hear as a difference between these?
Well, one of them would pretty much just be one sound, and the other one, or am I interpreting that wrong?
Well, actually they would both be just one sound, but they're going to have a difference compared to each other. Well, now I'm not a vocalist, but bear with me. If one was da, da, which one is the higher of the 2?
The bottom
The
one.
one with the shorter wavelength.
Yeah, the one with the shorter wavelength. And what you and I perceive is differences in frequency. The one with the shorter wavelength has a higher frequency. It has a higher pitch. So again, if this was do, do, would be the two sounds that we'd wind up hearing from it. So they differ from pitch, but they also differ in frequency. Well, we used these terms back in chapter 5, and what we said here was this. We said that energy is directly proportional to the frequency. And again, of these two patterns, the top one or the bottom one, which one has the greater frequency? The one on the bottom has a greater frequency, and therefore this pattern here has a greater energy as well, because energy and frequency are directly proportional to each other. Well, now, just like these vibrating strings fill up a space, and it's highly probable of finding a string somewhere in the space, these would correspond to, as if we were comparing these two orbitals right here. And so this one here being a simpler frequency, this one here being a more complex one, or a higher frequency. So if we compared energies of this one versus this one, which of these two has a greater energy?
The one with the two circles.
Yeah, this one here would have the greater of the energy. And if we were to compare the energy of these two, which one would have the greatest energy?
4.
Yeah, this one here with the 4 lobes. And these are actually only, about 8 of the different, or 9 of the different models. And we have some orbitals out here which are even more complex, many of which have 8 lobes on them, and they have an even higher energy still. So, in addition to size determining the energy, the other thing that determines the energy of an orbital is its shape. And so again, the more complex the shape, what can we say about the energy? The higher the energy. So the two primary determiners of the energy of an electron are the shape and the size of the orbital in which we find that electron. And so again, a vibrating string in this pattern is kind of like an orbital of this shape right here. Now, how does this get around the problems we had with the Bohr model of the atom? Because again, remember in the Bohr model of the atom, if we go back to this, like we looked at here the other day, we said that in order for the electron to move from one level to another, it could not exist anywhere in between, and we call that a quantum leap. It had to go instantaneously from one level to another, and when it did so, it gave off some light. Well, now, the way we get around that is this, is that we don't know the details of how the electrons move in any of these orbitals that are up here. They can move anywhere within here, they can move anywhere within here, they can move anywhere within here. And so, if we have an electron that's in an orbital of this shape, and it absorbs some energy, it's now all of a sudden able to move in an orbital of this shape. And this orbital, though, remember, has more energy than does this one. But if we overlap them, put these on the same x, y, and z axis, their spaces overlap, so what would happen then is that instantaneously the electron would go from moving in a space confined like this to in a space confined like this. But because their shapes overlap, we don't have to worry about there being a non-existence of the electron anywhere in between. It's just that they instantaneously go from moving in one shape or pattern to moving in a different shape or pattern. So that's how we go about determining the energies associated with the electrons. So what I'm going to do here actually is I'm going to check to see what you've picked up here. I think I got 4 or 5 questions in a row on the Socrative app. It's just kind of a review to see what you've learned. And so we'll start with the Bohr model of the atom. Remember, the Bohr is the simple one. And we said that it worked well only with which element? 5, 4, 3, 2, 1. Whoops. And we forgot to check. Worked well only with hydrogen. So it worked well only with hydrogen. Next question. It says that the energy of an electron in an orbital depends on which two characteristics of the orbital in which it resides. And there are two answers here. Select both of them. 5, 4, 3, 2, 1. Once again, they are the size and the shape of the orbital in which it resides. Good. Next up, an electron in an orbital has the most energy if the size of the orbital is 5, 4, 3, 2, 1. And that is if it's bigger. Remember that the larger the orbital, the more energy. The smaller the orbital, the lesser the energy. Think about dropping that wood block off the ground. The further we have that wood block off the ground, the more energy it has. The closer that wood block is to the ground, the lesser the energy. And number 5, an electron in an orbital has the most energy if the shape of the orbital is 5, 4, 3, 2, 1. And that is correct. The more complex the shape, the greater the energy. So this kind of wraps up what we're going to look at here in chapter 9. What I do want to make note of here is this. When we look at the study of all this, this is called the quantum mechanical model. So we can say that the quantum mechanical model is the currently accepted model of the atom. And again, that's what was developed in the 1920s. And the study of this stuff is called quantum mechanics. And so if you've ever heard of quantum mechanics before, what we just looked at is the study of quantum mechanics. Now, one of the things we are not going to do in Chapter 9 is this. Chapter 9, we will not be doing electron configurations. So I know some of you, at least in the morning class, were disappointed because you did them in high school and want to do it again here, but there's just other things we need to get onto, and we will not be doing orbital diagrams. So if you're looking ahead into Chapter 9, you will not be responsible for this stuff in Chapter 9, nor will we be using it later on in the course.